Our project was called @bots or @pots, classifying tweets as human-written or machine-generated. The goal of our project was to apply NLP and NLU techniques in order to classify a piece of text, specifically in tweet form, as human-generated or machine-generated. And this has a lot of applications. One of them is national security, as you've seen was really important recently, fighting harassment online, and cybersecurity, making sure that social media users are safe.
The dataset we used was a collection of over 7 million labeled Twitter responses, each generated by a machine or a human. The examples consist of an ID, a context, which is text that is always human-generated, a response, which is either human or machine-generated, and a label indicating who generated the response. Here we have a training example, and you can see the context, response, and in this case, the fact that it was a human-generated response. To tackle this problem, we applied 4 different models: SVM, Logistic Regression Classifier, and character and word level recurrent models. Our first approach was the SVM, and we took 3 different approaches within this, using unigram, bigram, and a combination of both features, Google News word vector features, and normalized bag of words part of speech features, trained on 10K examples and 1K validation. The best accuracies for each are reported below and hovered around 50 to 51.5% for validation and around 53 to 79% on the training set. So the SVM with these features did not perform very strongly, so our next approach was to instead try a logistic regression classifier. Here we used 2 different approaches. First, TF-IDF word features, and second, glove vector features on the same sized training and validation set as before. Here we obtained slightly higher validation accuracy, around 52%, on both of these models.
Next, we tried a set of recurrent models. The first type we tried was character-level recurrent models. Specifically, we used a bidirectional LSTM with trainable embeddings. We thought that a character-level model would be able to capture intra-word linguistic mechanics by using character positions instead of word positions. With this model, we achieved a 67% validation accuracy and a 65% training accuracy. Surprisingly, removing dropout and regularization got higher validation accuracy and training accuracy. And we'll have to see if this persists to the test set. The next approach was word-level recurrent models. For this, we expanded the dataset to train with 1 million examples and tried a suite of different approaches, whether bidirectional, unidirectional, or multiple unidirectional LSTM or GRU models, varying our hyperparameters over a broad range of different dimensions, such as the size of vocabulary or amount of padding. We arrived at a 67% training accuracy with a validation accuracy of 61% on the entire validation set. There were a lot of challenges. One is that training recurrent networks is hard, and we saw that training loss would decrease and then suddenly increase or explode, even when we used models like GRU or LSTM. We saw a large trade-off between the amount of data, the time to train, and how complex our models could be.
Another challenge we faced was feature extraction. This is particularly important for linear approaches, and in the future we intend to extract additional features to boost SVM performance. And finally, we wish to use pre-trained embeddings, such as Glove on IMDb or News, and train our own embeddings to boost performance on the model